Hi guys. So I'm alone right now, both in person and on Zoom. Doesn't matter. I am not technically savvy. Let's put it that way. I just discovered that about Zoom this morning. I've been a student my whole life, and I've never had to use Zoom to teach. So I had a lot of issues today. So instead, to heck with that, I'm just talking and give a brief description about what you guys need to do to get through experiment 2. And I'll send along my other first 2 videos as well, but this one's going to be very brief because there won't be any questions. So let's just jump right into it. Make this as quick as possible so you guys don't have a bunch of footage to watch. Students like to learn and they don't like to be bored. Alrighty, here we go. I'm sharing my screen with you guys. Alrighty, so experiment 1, you guys just had a worksheet you had to fill out and complete. All right, so this is the instructor only, instructor grade, or grading rubric for everything to come. And obviously, as you can see down here at the bottom with experiment 3 and 4, it's not as detailed as experiment 2 because it gets updated all the time. So don't think you have some sort of awesome secret gem now, but I just am here to help you as much as I can. So I'm sharing my screen with you. Anyways, lab reports. You guys have only done worksheets so far. Worksheets and lab reports make up the bulk of your grade. Quizzes are much less, so they are harder to retake. But I do have the power to exempt any of your grades and give you guys many attempts as you need to, as long as there's a legitimate forbearance on maybe why you couldn't submit or if something was submitted improperly, like technical difficulties. And I am here to help you, not work against you. I'm your friend, or I'd like to be. So if you have any issues, you're concerned about your grade at any point, I know you guys have a lot going on because you're taking a bunch of other classes too, and this is just the lab section of organic chemistry. I can help with also exams that you guys will have by the end of, I think, this month or maybe 5 to 6 weeks from now, at least your first exam. I'm great at chemistry. I love chemistry. So yeah, and I'm Matt, by the way. So you have 4 parts to every single lab report. Maybe there'll be a couple more for future lab reports if they're required, because some experiments do require additional input of data. But for this one, it's very simple. You have your abstract, procedure, data and calculations, and discussion. Now, the first 3 are important, but the 90% of your effort, time, focus, and attention is going to be on the discussion and conclusion. It revolves all the chemistry. You talk about all the chemistry involved, why things happened, and what your results mean to you. So for this experiment, you have steam distillation. So we've been focusing the entire time on trans-cinnamaldehyde, cinnamon bark. But what is steam distillation? So let's first talk about the chemistry involved. And the easiest way to go through this is to go from beginning to end. So we took a piece of cinnamon bark, X mass, and from that piece of cinnamon bark with a certain mass, we know from literature and past experiments, etc., that if the cinnamon bark is this mass, there's exactly this amount, theoretical yield, of trans-cinnamaldehyde contained within it. So if in a perfect ideal world, we were able to isolate all 100% of the trans-cinnamaldehyde, then we would get exactly this mass. Now, that's your theoretical yield, and that's calculable. You don't need to look at the experiment or you don't need to look at the experiment video or perform the experiment to get that data. So, your percent yield. Now, I discussed this a little bit in the last video, which is going to be kind of annoying to scroll through, so I'll go through this one pretty quickly. Say, for example, you have 30% yield. So what is that? You know how to calculate that because you did your recovered mass divided by your theoretical mass times 100%, and you got 30%. This is only an example. So explain not just how you got that, but what does it mean to you? And what that means is that during the isolation of trans-cinnamaldehyde from cinnamon bark, I was able to recover exactly 30% yield, meaning that 70% yield of the trans-cinnamaldehyde that was in there was lost along the way. Or you can reverse extrapolate from 70% and figure out, or just take the theoretical yield minus your recovered mass to find out how much mass was lost. And then you can say like X mass of the trans-cinnamaldehyde was lost from step 1 to the end of the step, or from the step 1 to the end of the entire procedure at step X. And why? And a lot of the time it's because of human error, but there can be some more technical chemistry boundaries that are lot more difficult to cross. Say some experiments are more difficult than others, and so a yield of maybe only 45% has ever been achieved in all of history and chemistry. So you expect to see a yield of 45%. That wouldn't mean it's bad. That just means you're doing as well as every other chemist who's ever performed that, including all the famous ones. So there you go. So anyhow, what it means to you. So we're done with that. I recovered 30%, 70% was lost due to human error and these other possible things that might happen. Let's say like some things that might happen, or you drop your flask. Some of it remained in the pipette when you were transferring. The tiny, tiny little things like that can affect your yield, and that's what you want to write about. But how does it work? So I described this before, a pretty decent analogy, I thought. But since this is the bulk video, I'll just go through it again. We boil cinnamon bark in water, and we extract the trans-cinnamaldehyde. When you make pasta, a lot of people think that you just put it in the water, you boil it, and the water goes into it, and then that's what you're eating. But that's not the chemical process that's happening. When you make pasta, all the ingredients you need to have the soft, squishy macaroni there that you're going to eat at like 1:32 in the morning after you're with your friends, it's all right there. The only thing holding it back is the starch. So there's starch contained in this dry pasta, and you need to remove it by adding this pasta to water and increasing the boiling point until it gets to a point where the starch becomes soluble in the water, goes into solution, and then when the water boils off, starch doesn't boil off with the water vapors, but same principle, you boil cinnamon bark, trans-cinnamaldehyde comes out of the bark, just like starch comes out of pasta when you boil it, and trans-cinnamaldehyde does travel with the vapors of the water. And the reason starch doesn't and trans-cinnamaldehyde does is because trans-cinnamaldehyde is an oil at room temperature, whereas your starch is going to be solid at room temperature, so it just affects solubility a little bit. But same principle, spaghetti, cinnamon bark. So you're boiling water, and your trans-cinnamaldehyde and your water vapors are raising up as it boils, and now the glass above your reaction vessel is a lot cooler than the glass below, so it's going to condense on the walls of the glass, just like when you have a hot drink on a cold day. So you're going to have liquid droplets forming on the gas and falling back down, collecting into your well. And that's what you're extracting with your pipette. Now, you want to talk about the chemistry. How are you able to extract and work up your product? So you now have an organic trans-cinnamaldehyde product sitting in water. So what are you going to do about that? Because we need to get rid of that water and isolate our trans-cinnamaldehyde so we can get a weight and figure it out. Now, what we know is trans-cinnamaldehyde is organic and water is aqueous. We know that organic dissolves in organic and inorganic dissolves in inorganic. So when you have table salt, sodium chloride, NaCl, you can put it into water and you'll see it will dissolve. Now, if you have something organic like benzoic acid, which I demonstrated on what I showed on ChemDraw in the last video when I was demonstrating ChemDraw, then that's not going to dissolve in the water. You'll have powder, you'll drop it into the water, and it won't, as much as you stir it, it will never go in. It'll have like a snow globe effect. It doesn't want to go into the water. Take that same organic compound, drop it into an organic solvent, like the one we use, I'll use an example, methylene chloride, it'll go right in. So you have an organic compound, goes in water, doesn't solubilize, still there as itself, as solid. You have an organic compound, it goes in the organic solvent, aka methylene chloride or dichloromethane, goes right into solution and dissolves. So now when you add methylene chloride to your solution of water and trans-cinnamaldehyde, it'll form two layers because the aqueous and the organic they're immiscible, we say. They do not want to mix together and form one solution. So you'll have two layers, one of the more dense solvent and one of the less dense solvent because they are not going to mix. Now we know methylene chloride, our organic solvent, is more dense than water. So it's going to be on the bottom layer. And once you shake it up, you're going to get all of your trans-cinnamaldehyde organic compound to favor the organic layer as opposed to the aqueous layer because we have an organic compound. So if we have an organic compound, where would we expect it to prefer to dissolve? In an organic solvent, aka the methylene chloride on bottom. So once you add methylene chloride, the trans-cinnamaldehyde moves from the aqueous layer to the organic layer, And then by extracting the methylene chloride with a pipette, digging through, pulling it all up, and then adding a drying agent, filtering it out, we now have a dry, and dry meaning absolute, it can still be a liquid, but dry just means no water. So you have a dry, aka no water, solution of methylene chloride with your trans-cinnamaldehyde dissolved inside. So there's a nice description of the chemistry involved to help you write this discussion and conclusion. Now, let's see here. Now you want to get rid of your methylene chloride. So something I mentioned in the last video, but I didn't mention here, I'll talk about it now. Why do we want to get our organic compound into the methylene chloride? Like, what are we doing with that? Why can't we just have it in the water and then isolate it and use that? Well, the reason we want to get it away from water and into methylene chloride is because water boils at 100 degrees Celsius. Methylene chloride, I mentioned this previously. I have no idea what I'm talking about. Because most of the world aren't chemists. Okay, 40 degrees. So let's go back to my rubric here. So your water is going to boil at 100 degrees Celsius, but your methylene chloride boils at 40 degrees Celsius. So if we can extract our trans-cinnamaldehyde from the water into the methylene chloride, then without having to increase the temperature to 100 degrees Celsius, and it's important to know that's an aggressive temperature. You wouldn't put your finger on a stove if it was 100 degrees. You'd be like, that's going to hurt. So 40 degrees is a very mild, and this we're talking Celsius. So if we go back here, what was it in Fahrenheit? 103 degrees Fahrenheit. So, I mean, I guess, no, that's tolerable. You can put your hand on that. It'll be just fine. So 39.6 degrees Celsius is the boiling point of methylene chloride. So if you introduce too much temperature to an organic compound, it'll turn black and char. That's just called degradation. It just really gets all yucky and transforms from its actual chemical structure to something just like a coal, like destroyed bubbly black mass. That's called degradation. So you don't want to apply too much heat to your product. So once we get it in the methylene chloride, we can easily, with almost no energy at all, boil off all the methylene chloride, and then what's left? Trans-cinnamaldehyde. There we go. So now we have trans-cinnamaldehyde, and we have chemically removed all the water and thermoenergetically removed all the DCM. So now you have your crude, isolated trans-cinnamaldehyde. And from there, you're able to, typically we'll let it dry overnight because we can extract methylene chloride, but you know, we can't look at it under very complex, intense microscope and check every single molecule in solution and make sure that there isn't methylene chloride in there. So what we do is we just leave it overnight. This is what happens if you have a little petri dish of water and you leave it out overnight or a few days. It'll evaporate. You'll have like little crusty things if you get some dirty tap water, something. So same idea with methylene chloride. The water boils at 100 degrees Celsius and still manages to evaporate after a day or a couple days sitting out. Methylene chloride will only take an hour, a couple hours, but we leave it overnight to be thorough. So then you come back the next day, all the methylene chloride that you can't see has evaporated, and you now have your dry, crude product, which you can weigh and take the melting point of. And now I explained a little bit, now you want to talk about your melting point, and I'll go over that. That'll be the last thing, or I'll talk about the IR too very briefly after. But the melting point, now you check your melting point. Now I am not, this is an arbitrary number. I'm not looking at the worksheet right now. I don't have it in front of me, and I don't want to go digging for it because I don't know what's on my laptop. But melting point. So say your literature melting point, the one that is in your lab manual, says, okay, your product is going to melt from 46 degrees Celsius to 48 degrees Celsius. Now you take your sample, and let's say it melts at 42 to 44. So instead of 44 to 46, or 46 to 48, like to lower. So how can a melting point be lower or even higher? Same thing, let's say it's like 50 to 52. And what does that mean? So if your trans-cinnamaldehyde is absolutely pure, And we know this because industrial level chemistry allows us to acquire industrially pure compounds and test them for these properties. So if you have an industrially pure sample of transaminaldehyde, it will melt at between X degrees Celsius and X plus n degrees Celsius, this small range. Usually varies about 1 to 2 degrees Celsius. Now, if your melting point has your experimentally recorded, tested, and observed melting point is slightly lower or slightly higher, this means that you have some impurity. That means that, and by impurity, I just mean anything that's not trans-cinnamaldehyde. That's all we theoretically want. And it's not a bad thing, because, you know, it's really, really hard. You can't get 100% pure product, right? It's really, really hard. But what we can do is, it depends on the impurity, but what that impurity is can do one of two things. It can either raise your melting point range or lower it, right? But it's going to raise or lower it relative to what it actually is. So you can say, all right, my melting point range was 42 to 44, but the literature was 44 to 46. So this indicates that my trans-cinnamaldehyde is very close to being ultimately pure, but still contains a small amount of impurity, which you cannot put a number on. You cannot calculate the impurity or how much impurity there is or what the impurity is just from the melting point. We can infer what it might be, but we cannot know. So that's all I'm looking for when it comes to melting point. Just share with me the literature, share with me your experimental melting point. I will provide it in most cases. Sometimes I'll just let you guys use Zach's, the one that he used in the video. But just tell me what it means. And it's going to be the same description almost every time. The melting point was this much higher, my melting point range was this much higher or this much lower. And because of this, my product is very close to purity, but not quite so. There are some impurities because the melting point isn't perfect on the literature. If it is, you can say, wow, I have a great product, maybe 99%. Like, put that in there. I love to read about that. If not, I love reading about errors too. We learn with our errors. And that's melting point. Now, I'll quickly go over IR discussion. I'm getting a lot of emails because I bet people are trying to join this call right now because I have no idea how to make it open. And I haven't checked because I want to just make sure I get through this because I've already gotten halfway through it twice and gotten cut off by Zoom. I don't know why it does that. But anyways, last bit, IR discussion, infrared analysis, infrared spectra, infrared data. This always gets everyone. No one knows what the heck an IR spectra is. Everyone always sees it at the bottom of all your experiment procedures from the lab notebook. Everyone's like, I have no idea what the heck this weird graph means with this weird line. Like, how does this correlate to anything that I did or anything I learned or anything I read or anything I isolated in my experiment? Doesn't make sense. So let me see if I can pull up an example actually. Sorry, I got Young Gravy's new song stuck in my head. Is this Blackboard? Yep. Okay. And I was going to show you IR. Gosh, this Zoom menu at top is so obnoxious. Go away. Let me live my life. Okay. Week 3. And click here. I don't know if this is good. Just click it. Click it. Oh. Sorry, Zach. Don't need your help. I don't need to listen to you right now. Here we are. Alrighty, ladies and gentlemen. Here's an IR spectra. Okay. So this is going to be the IR spectra for your trans-cinnamaldehyde. People always want to know what the heck this means. I wrote a 35-page report for my instrumental analysis final on infrared, gathering of infrared data. So I can help you with this, and I will make it as simple as possible, because that's what it is. It is simple. Essentially, I'll give you the quick rundown. Look at my mouse on the screen. This area of the IR, your IR spectra will always look like this box. It'll have percent transmittance, which means transmittance is how much light passes through something and is not absorbed. So, and then you have it by wave numbers or inverse centimeters. So let's start with what IR is. So you take an IR spectra. IR, infrared spectroscopy, is a branch of spectroscopy. Spectroscopy is the process of characterizing organic compounds. Because what is an organic compound? We have structures that we like to draw between carbon atoms, oxygen atoms, hydrogen, et cetera, et cetera. But how do we know that they are the shape that they are? Like, did someone just make up all these structures one day and put them on a book and make up organic chemistry because torturing people is fun? No. We take our compounds, our pure compounds, and we put them in a machine. This machine berades them with light, and how the compound reacts to that light is how we infer the structure of said compound. So in infrared, we rely on infrared spectroscopy to give us an understanding of the functional groups on a compound. So there are other forms of spectroscopy that can give you more detail, the individual atomic connections between atoms, so that you can draw the structure as explicitly as possible. But infrared just gives functional groups, and you'll learn more about functional groups as the semester goes on. So let's just look up really quickly transformaldehyde real quick. It's hard. Turd. Here we go. So something you might be looking for. All right, we have this aldehyde group here, we have this double bond here, and we have this aromatic benzene right here. So when we're looking back at our IR, you're going to have two sections essentially. This section on the right, usually it's always going to be about below. And notice on the wave numbers, they go backwards from 4,000 or 4,500 all the way back to 0. So your x-axis goes backwards, not as intuitive. And that's just because it's inverse centimeters. If it was centimeters, it would go up, but it's 1/centimeters, so it goes backwards down. So the right side of your spectra is always going to be jumbled peaks, and that's the fingerprint region. That's the detailed region. If you really want to break down the spectra with math and algorithms and programs, that will help you pinpoint some of the non-polar hydrocarbon regions of the molecule. We're not going to focus on that. Most people don't even look at this. Most people just gloss over this, okay, whatever. What you first want to pay attention to is this very tall arching peak right here, all right? So the first peak you're going to see right here, the tall one, usually around 1725 or 1650-ish, inverse centimeters, wave numbers, is going to represent your carbonyl, all right? So when we go back to cinnamaldehyde, this is your carbonyl. Of your whole molecule, you have carbons around here, carbons on a chain, and then a carbonyl here on your aldehyde. The carbonyl is simply the C double bond O. It pays no attention to this hydrogen over here, it pays no attention to these carbons over here. They're arbitrary. We're only talking about a carbonyl group right now. A carbonyl is a carbon double bonded to an oxygen. And that shows up very strongly on an infrared spectra. Get this manual away at that 1650 to 1725 region. So right here. So in your discussion, mention that. Okay, I knew that I had, this infrared spectra applies to my product because you can see the peak for the carbonyl, the C double bond O, right at, what is this, 1655, I think it is, or 1711 on the bottom screen. And then over to the left here, this is the region we like to pay attention to. So this is the region where we're going to find evidence of our functional groups. So say, for example, if you have, this is what we do have, and this represents our trans-cinnamaldehyde, and this represents our double bond. However, it's not very interesting, tiny little peaks over here, even though it's the bulk of what you're going to write about. If you had something like an amine, okay, that's a nitrogen. So a single amine, a primary amine, is an NH2 coming off of some molecule. You ran an infrared of that, your NH2 should show up right around here. If you look where my mouse is, the end of that spectra. And then, so that's just to give an example. So functional groups like to peak when they're exposed to certain radiation, light, electromagnetic spectrum radiation, because you shoot something with radiation, aka light, then it gets excited, the energy state goes up, electrons get excited, and then almost immediately also they come back down and they release a certain amount of energy, and we can read that energy output, and then reverse extrapolating it using several different algorithms, mathematics, and programs. And that is how we end up with this spectra, and that is how we are able to extrapolate what functional groups we have and confirm our product is our product using infrared spectroscopy. So when you look at this spectra, you'll say, oh, I know this is trans-cinnamaldehyde because this peak right here represents the carbonyl CO stretching, and that's what it does, it stretches. So when you shoot infrared light radiation at your compound, the bonds will react. Like I said, they gain energy, they jump to a higher energy state, they'll stretch. So your carbonyl peak will stretch and then recondense, releasing a certain amount of energy that we can read right here. So we know that that's our carbonyl. And the same thing with the double bond. So double bond will also have a stretching, bending sort of reaction to the infrared radiation, and its release of that energy, or the way it augments as a result of that energy, is represented right here as these peaks. This 2813 and 2742, and down here as your 3004 and 2959, or whichever number that was. Pretty hard to read on the screen. Yeah, that's the bulk of that. And I have been getting emails. I am truly so sorry to all the students that are emailing me right now and having trouble getting through about their questions. I'm going to answer all your questions as soon as I'm done recording this video and send it out. But I just wanted to get through a quick recording of what lab reports are. And this was a long recording, guys. I know, it's a pain in the butt, but it's your first lab report. And lab reports are a lot more than worksheets. They're worth the same amount of points, but it's a lot more work. And as I said before, 90 to 95% of your attention and focus and work is going to be on this one section, discussion and conclusion. Calculations take a minute, all right? How long does it take you to punch recovered ASA divided by theoretical ASA times 100 in your calculator and then put it into a Word document? Not that long, and it doesn't take that much mental acuity and effort. Now, your discussion and conclusion is where you're going to need to, and that's only, and I don't want to belittle anyone who's having issues with calculations. That's totally normal and natural and fine. Everyone's going to have issues with calculations. I'm saying if you're very adept at performing these calculations, then they don't take quite long. Now, the discussion and conclusion is going to be new to all of you because you're all new to organic chemistry. And that's why it's going to take so much time, because you really need to stress, I'm grading you. I am giving you points, and I have the power to take away points. I'm not some vindictive, anti-benevolent, like crazy guy who wants you to do that. I want you to do extraordinarily well. And so I'm telling you, get the point across that you understand the chemistry of the reaction, or the experiment. When you finally get to your discussion and conclusion section, it's very tempting to think, okay, well, the whole point was just to get trans-cinnamaldehyde from cinnamon bark. No, that was the example we chose to demonstrate to you the process of steam distillation. So prove to me that you know what steam distillation is, how it's used, and how chemists, like why chemists would want to do it. Make that clear to me on top of, knowing why you're, on top of your understanding of the procedural analysis, like how does reflux condensing work? The water's hot at the bottom, vaporizes, goes up, cold glass just like on a cold glass on summer day, recondenses into the well. Procedural chemistry explanations, like we all went over already. But the main purpose is to make sure you prove to me that you understand the chemistry going on. Trying to think of any other questions I might have had to answer before I tune off. I'll be available throughout the week for questions. I'm sure there will be many. I still have a lot of worksheets to grade. I haven't started, so it's going to take a little bit of time. And yeah, you guys will have a lab quiz due at the beginning of each week or whenever you guys are ready. I know you guys have 15-minute intervals on that. And then worksheet due at the end of that week or the week after. You can always check the due dates, the most recent, the most upcoming due dates on the syllabus on Blackboard. But keep in mind, those due dates are not adamant. The only one that you can rely on is the one that's coming next, because I know from past experience over the years, Poulos loves, doesn't love to. It could be a perfect world. Who wouldn't want a perfect world? But we end up in a situation where days don't totally match up and sections don't totally match up. And those due dates will change. They're subject to change, and they will. So, always be checking the syllabus, because it's going to be quite a shock if you find out that something you haven't started is due tomorrow as opposed to next week. So, yeah, keep that in mind. I can go over questions that you guys have at any time. I'm here to help. I'm a resource for you guys. Shoot me an email anytime. I will schedule these Zoom meetings way more in advance next time, because I know we have students that are asleep because it is like 1 a.m. wherever the heck they are in the world, because we are talking to people all over the world right now. So yeah, that's it. I'm Matt. We're gonna have a great semester. No one panic. It's gonna be fun. Do some chemistry, guys.